In this video, I'm going to talk to you a bit about just some of the basics of trigonometry, which is our next topic. Now, you're going to spend quite a lot of time looking at trigonometry and circular functions in maths methods. So in terms of the basics in Specialist, we go through them relatively quickly, and you'll get a lot more detail in your methods class. But just to begin with, so just some points as to why we study circular functions and trigonometry in maths. Well, they come up all the time. In fact, they're shockingly frequent. So things like a light wave, if you already know what a sine or cosine graph looks like, you could probably recognize them just there. That's one way to model them. Also, I mean, anything with a repetitive element to it, anything that's what we call periodic, can be modeled by circular functions. So the tides, for example, here, they are periodic, as you probably are well aware, and they make a sort of circular function in their own way. Likewise, human heartbeats, while they don't look like sine or cosine graphs, they're actually just the addition of several different circular functions, and you get those perhaps a bit familiar graphs of heartbeats, which is kind of fun. And it all boils down to the unit circle, which is what we're going to start with today. So the unit circle, it's called that because it's got a radius of 1 unit. And so if you've got your x and y, you've just got, here's your circle, it's got radius 1 as shown, and you know all those points, like on the x-axis you've got it hitting 1, 0 and minus 1, 0, for example. Now, if we want to measure angles, we measure them from the positive end of the x-axis. So here we've got some angle, looks to be about 30 degrees, right? And if we were, straight up here, it'd be 90 degrees. Conversely, if we had a negative angle, so say we had negative 30 degrees, well, assuming this is 30 degrees, then negative 30 would be about down here, wouldn't it? Negative 30 degrees. And negative 90 would be here, going that way. So they go clockwise for your negative and anti-clockwise for your positive angles. Okay. We also, just as a convention, we number our what we'd call quadrants. So here we've got x and y, where both x and y are positives. So all our x values here are positive, all our y values here are positive. That's quadrant 1. And then we go around in an anti-clockwise fashion, like our positive angles. So quadrant 2 is just the next one along. So x values are negative, y values are positive. Then down in quadrant 3, we've got both x and y being negative. And in quadrant 4, we've got just y negative and x positive. Now, one thing that we can define, and we're going to play around with this a bit, is that the sine of an angle, so in this case, we've got the angle is t, which we can see marked here. The sine of an angle is the y value corresponding to the point on the unit circle. So here we've gone around an angle of t degrees. And when the point on the unit circle is there, and its y value, so up here, however tall this is, whatever the distance is from the origin up to this y value, which we're just keeping general as y, is what sine of t equals. So we've got sine of t is equal to y. Likewise, the cosine is whatever the cosine of that angle is whatever the x value is there. So we can see for whatever value of t we've got here, so here's the x value, x, just keeping it general, that distance there is cos of t. So if we were to approximate that, well, we know that here is 1, so what it looks like cos of t is about 0.75, and cos of y looks about quite similar, doesn't it? I mean, maybe a bit less, 0.6, who knows? Just keeping it general. So those values don't really matter, I'm just making them up. Now, you probably remember from earlier in maths, the mnemonic, the memory device, SOHCAHTOA, so you can remember how to get side lengths or angles of right-angled triangles. Keep in mind, these only work with right-angled triangles like this one here. And we just use that memory device, so O for opposite, A for adjacent, H for hypotenuse, and each of them work like that. Now, something that perhaps you might not have been shown when you did SOHCAHTOA in years gone by is about how come these ratios work for every possible right-angled triangle. Now, one nice way to do that kind of in a practical way, though it's not very general, which, so you know, in specialists we like to keep things general, but I can just show you how you would do it. So say you were to draw on a piece of paper a right angled triangle of some angle. So say, you know, you drew this on a piece of paper and that came out to be 20 degrees. Then what you want to do is you just drop down a couple more of these vertical lines. And so you get these smaller right angled triangles, right? And all you need to do is compare the side lengths and see that the ratio of these things, like say the opposite and the hypotenuse, the ratio of whatever the opposite and the hypotenuse are, stays the same. So for example, the ratio of this to this, so that's opposite of 20. Oh, it's not the hypotenuse though, is it? That's the adjacent. So we're talking about tan here. But for example, so the ratio of that opposite and that adjacent, would be the same as the ratio of this with this bigger one down here. A bit hard to tell where I'm just using one color. But so that'd be a practical way you could do it, by just drawing it and then calculating it using a calculator. But if we want to keep it really general, we can think about the idea of similar triangles. So if you don't really know your similar triangles, then this explanation is not going to be very helpful, and I would just skip ahead, but I'll just do it for those who do know. So you'll recall with similar triangles that, so here we've got similar triangles, right? Because all their angles are the same. They've got a right angle or right angle, and then this angle is shared between them. So the other angle, knowing that angles in a triangle add up to 180, must be the same. So they're angle, angle, angle similar, and or AAA. And so that means that if I know the scaling factor of how much bigger the triangle OBC is to OB-C', then I can just multiply side lengths of the smaller triangle by that scaling factor, and I will get the size of the other one's corresponding side, right? So in terms of getting the scaling factor, well, it's just the ratio of any two corresponding sides. So the hypotenuse of both triangles corresponds. So I know that the scaling factor is equal to the ratio of OB on OB dash. So the big line and then the small one. But notice OB dash is just 1 because it's part of the unit circle. So I've just drawn it into my bigger triangle, OBC. So I know that the scaling factor is just OB. And now also I know that, for example, OC dash, if it's in the unit circle, then this is just going to be cos of theta. The distance OC dash is cos theta, and this one is sine theta, B dash C dash, because it's in the unit circle. So that means that this one, BC, is just OB times sine theta, because that's the scaling factor, it's just that much bigger. And this distance down here is OB times cos theta. It's going to equal to OC. And so using that, I can rearrange and get things like this, that cos theta is just OC on OB. So it's just saying that the cos theta is going to be the adjacent over the hypotenuse. So we're just seeing that it's generally true, those SOHCAHTOA things, that they're generally true for every triangle, well, every right angle triangle you could possibly imagine or create. Okay. The next thing I want to talk about is thinking about when we've got angles bigger than 90 degrees, or obtuse angles. If we look at the unit circle, well, we can see a couple of relationships. So say I've got an angle here where I've gone bigger than 90 degrees. So if this is theta, and this angle here is 180 minus theta, so I've also got theta in there, seeing as I know that all the way over is 180. Well, I can tell pretty quickly that, so I was told that the y value is sine of theta. And we can see that on the other side at 180 minus theta, that y value is exactly the same. So I know that sine of 180 minus theta is just exactly the same as sine theta. And then likewise, well, in a kind of similar vein, we said that this distance was cos theta, right? The x value. And over here, if it's that angle in there, then we're going to get that is just negative cos theta, right? We're on the negative side of the x-axis. So I can say that sine of 150 is just exactly the same as sine of 30 because that would make that work. And cos of 150 is just negative cos of 30. And yeah, and as it happens, those are exact values, so we could even get them exactly. One of the last things we're going to look at is just, so tan theta, we define that as it's sine divided by cos. And then I've got here some examples of finding things like angles and side lengths, which you can go through if you like, have a look at how it worked, but it's just setting up that SOHCAHTOA, which you should be pretty comfortable with. And then finally, just a little kind of memory device we use to think about when our ratios will give positive and negative. So if we think about it in the second quadrant, we had that sine was positive and cos was just negative. And if you think about putting that into tan, well, you got tan theta is sine over cos. So if you put in, well, sine is always going to be positive in this quadrant, and cos is always going to be negative. So if you always have a positive divided by a negative, tan's also always going to come out negative, much like cos. So only sine in this quadrant is positive. Now you could follow that logic through in the other quadrants and realize that where each of them is going to be positive, and where, so here everything's going to be positive, in the second quadrant just sine, in the third quadrant just tan, because you've got a negative divided by a negative, and here you've got just cos being positive. Now the way to remember that, there's a couple of ways. Some people like to call it the cast rule because you could write it out like this, C-A-S-T. I don't entirely love that because it starts in the fourth quadrant, which might be a bit confusing for some. I like for my students to make up their own memory device. So my memory device is all students think creatively to remind me to write it as A-S-T-C. And your job is to creatively come up with your own. For example, one of my students, when he learnt this, it was his birthday and his name was Sam, so he had all Sams today celebrate. Isn't that nice? Okay, we'll leave that there for now.